Okay, so now I'll start. So today, as per given the Google Forms, what was their fracture mechanics now today?
Sir, actually, that timetable has not been updated, so we don't know what topic is to be taught today.
Okay, and then in last in this week there was any last classes of like on Wednesday or yesterday or Monday?
Yes, sir. Sir, on Monday, there was a class on transport phenomena, sir.
Okay, that schedule was there.
Yes, sir. That schedule is there.
Okay, then Saturday.
No, sir. There are no classes on Saturday. Just now from 6 to 7, there was again a class on physical metallurgy.
Today or Saturday.
Today, sir. Today, 6 to 7.
Okay. But I had formed the filled the Google form. That was I had given fracture mechanics for today.
Okay, sir. Let's continue with
Hmm.
this window.
Okay, so first let us understand what is brittle fracture. This is also called cleavage fracture. What happens here? From grain to grain, it is different. The cleavage plane is different. So it happens something like suppose we have a crack here. And these are the grains. Suppose the crack in one grain. Suppose this one is suppose a cleavage plane in crack one, in grain one in this grain. So in this it might change to something like this different plane. Then again in this grain it can go something like this. Okay, so all these are cleavage planes for each different grain. And this plane, which plane will occur, that depends on the surface energy. Okay, so this is why we see faceted surfaces in brittle fracture. And it is flat, that's why good reflectors of incident light, that's why it appears bright. Okay, In ductile fracture, what happens? We have many small particles like inclusions or some precipitates. So these particles, first there is decohesion of the particle and matrix surface. Then what happens? Void formation. In those regions where the particles are present. Then void coalescence. So this is called, first it happens like micro necking, when small voids they form and they coalesce. This term is called micro necking. After that we have visible necking because of this, that is in macro scale. Then fracture. So if you see the ductile fracture surface in SCM, if you go to high magnification, you will see there are very small particles inside the voids. Those will be clearly visible. Now let's go to fracture. Suppose we have a material So we're applying stress in this direction and there is a crack which is, this is our A and this length is B. Okay, so first English, he was a scientist, so he proposed that the sigma max will be sigma applied, that is this one, one plus 2 A by B. But here you can see as B becomes smaller and smaller, this becomes infinite, and it suggests that no matter can sustain small amount of load when crack is very sharp. But we see materials with cracks and all this thing, they don't just break. So there is something that is explained by Griffith. So he suggested a crack will grow this is the key of his theory. rate of change of surface energy is equal to rate of change of strain energy. Okay, so there are two terms. Strain energy. So if someone asks what is Griffith's theory, you should say this line only. This is the key. So what is strain energy? That you can derive using dimensional analysis or those, but you don't need that. I am just writing that directly. This is the strain energy, and this is thickness. B is thickness, A is crack length, and this is applied stress, and this is Young's modulus. Okay, for unit thickness, if you assume unit thickness, then it is 1. So you can write it at pi sigma square A square by E. Similarly, you can write this one is clear na, Griffith's theory, what I wrote here. Because what crack has to propagate, that means sufficient energy should be provided to create new surfaces. Two surfaces will be created when a crack is propagating. So we have sufficient energy to propagate the crack, then only the crack can propagate. So this is the crack driving force or strain energy. This should be equal to the surface energy, rate of change of surface energy, then only crack will grow. So this just comes because you have two surfaces, 2 into, again this you can assume as 1. This is the surface energy, gamma s. So 4a gamma s you can write. So you can just differentiate this. This is your strain energy and this is surface energy. So you have to differentiate with respect to 2a. Okay, because we take the crack length as 2a always for a central crack. So just differentiate the two values that I have written. So from that you will get the relation fracture strength So this one is one important relation. Most of the GATE questions are based on this. Another is the theoretical cohesive strength. Okay, this one also remember. This is when there is no crack. What is the theoretical strength that is required to repapart a material and there is no defects? So this is our interatomic distance.
Sir, actually your slide is not visible.
Not visible.
Sir, means it has stuck on a particular moment.
Oh, okay. Now it's visible, no?
Yes, sir. Now it's visible. Yes, sir. Yes,
sir. So I have written that here you just have to differentiate the strain energy and the surface energy. The rate is equal. When the rate is equal, then only crack will propagate. And from that you calculate this. This will be derived from that relation only. And this will be your critical crack length. And one is theoretical cohesive strength, that is when E gamma is by A0. This A0 is your interatomic distance, this gamma is your surface energy, and E is same elastic modulus. This is when there is no crack. What is the theoretical strength you required? You need to repapart the material without any defects. So the resultant curve will be like this, where this is the critical. So when the crack length is below AC, there will be incremental crack growth. When that is A equal to AC, catastrophic failure. This is an important term, energy release rate. This is denoted as G1. So what is this? This is just as we have discussed in the first differential of del UA by del 2A. That is basically this is also called crack driving force. The definition is this: energy released per unit extension crack front of the body per unit crack tip. That's why this 2 comes here. Okay, the energy release per unit extension of the crack front per unit thickness of the material of the body per unit crack tip. And this is the relation. Similarly, another term you might have heard, resistance or R curve, that is just the surface energy term. Okay, so this remains almost constant in brittle materials because there is no plastic deformation. When plastic deformation is there for ductile materials, it gradually increases with increase in crack growth. Okay, because plasticity will be there, plastic deformation will be there, crack tip blunting will be there, so that will increase the resistance for further crack growth. I can't teach all the things here. I will go to some important formulas that are frequently asked in GATE. Okay, one more thing. Do you know what is plane stress fracture toughness and plane strain fracture toughness? Like, first let me define fracture toughness, what it is. This is the critical value of the stress intensity factor. So what is stress intensity factor? So you might have seen in DETR also sigma x, sigma y, sigma z, k1 by 2 pi r. And there are some relations related to sin theta and cos theta, big equation, sin theta by 2, cos theta by 2 and all those. So this one is your stress intensity factor. So it describes, like theta is there. So if there is a crack in any body and we want to find the stress field around, suppose here or here or here, so specifically there will be specific theta for that. So according to that we can find the stress field at any point using this stress intensity factor. And when it reaches a critical value, when K1 reaches a critical value, catastrophic failure. So basically we have three modes of failure: mode 1, mode 2 and mode 3. Generally we consider mode 1, that is crack opening mode. This is forward shear, this is parallel shear. Okay, so we consider this model, so often we write it as K1C, that is critical value of stress intensity factor in mode 1. So the important formula that are relevant for gate are: first, K1C Y sigma pi A. This is the geometric factor. For surface crack it is 1.12. For center crack it is 1. That's why surface crack is more severe. And this is the applied stress. This is the crack length. So question will be given. Suppose the geometry factor is 1, K1C is given, A is given, what is the stress applied? So you can find this. Or if these three will be given, you can find out the crack. And remember, this is the critical crack length. For this specific stress value, this is the critical crack length. So if stress value changes, the critical crack length will also change according to that. Then plane strain fracture toughness. In this what happens? Suppose we take the material fracture strength versus thickness of the material. Okay, so we will see that the graph goes like this, and after some thickness it becomes constant. So this region comes under plane strain, and this region is plane stress. So in plane strain what happens? Suppose we have a crack as the thickness of the material increases. Suppose the crack tip stress is high at the crack tip, so it wants to deform plastically, but it has a larger elastic area region that is around it, so that will not allow it to deform plastically. So there will be a small plastic zone. Again, there are so many things in this, like plastic zone also you have to see first. This one, this RP you can consider, this will be the size of the plastic zone. Okay, so but when the thickness is low, that is in plane stress region, what happens? So this is the thickness of the material, but this is here, this is the thickness of the material. So around the crack there is a large amount of material that has to be deformed plastically if the crack tip has to deform. But here, as the thickness is small, there is small amount of material that has to be deformed plastically. So there will be plastic deformation, and the crack tip plasticity, the plastic zone size will be higher. So but this is for plane stress, and this is for plane strain. Remember, the plastic zone size for plane stress will be always bigger as compared to plane strain. Also there is formula for that derivation, I won't go into that. or plane strain by 6 pi. Okay, so this one is smaller, so it is for plane strain and this is for plane stress. To derive these relations, first you have to see this sigma x, sigma y, sigma z will be given as terms of k1 by 2 pi rp sin theta by 2 cos theta by 2, some big relations will be there. So from that you have to calculate the principal stresses, sigma 1, sigma 2, sigma 3, like that we do for Mohr circle, that in elasticity or plasticity, that chapter. So you have to calculate sigma 1, sigma 2, sigma 3. Then you have to apply von Mises criteria. Okay, then you will get into find these relations. So I'm not going into that because that is not required for GATE. If you go for higher studies, you will know these things. So these things you remember. The plastic zone size for plane strain and plane stress. And another thickness dependence B equal to 2.5 K1C by sigma y square. This one is also important. This is for plane strain condition. What is the minimum thickness required to obtain plane strain condition? This is the thickness. Suppose in question this will be given, K1C is given, sigma ys is given. What is the minimum thickness to obtain plane strain condition? So you have to use this formula. Clear till now? I have two questions. I have taken other fairly easy questions. Okay. What is that question? Okay, so this is one question from GATE. A rope, it is, the slide is visible, no?
Yes, sir.
Okay. So a rope is attached to a glass sheet 10 centimeter wide and 0.127 centimeter thick, containing a central crack with a total length of 1.62 centimeter, that is oriented parallel to the ground. Fracture toughness is given 0.83 MPa root meter. What is the limiting load that can hang from the rope? Okay, so how to try this? We know.
So like we can calculate the stress by dividing the load and the cross sectional area together.
First you have to find out the stress. This is given. This is given. Crack length is already given. So you have to divide it by 2. Okay, because central crack, remember central crack you have to always take divided by 2. If it is side crack, then you can take this full, but if it is central crack, you have to always divide it by 2. Otherwise the answer will be wrong. So first K1C is given, A is given, you have to find sigma. Then from sigma you can find out, like the width is given, what, glass sheet 10 cm wide. So this is the glass sheet, this is the crack. Okay, then you have to find out the cross section area of this surface. Okay, 10 into 0.127. Okay, so first you find out sigma using this relation. K1C is given, A is given. Find out sigma, then we know sigma equal to F by A. So what is A? Sigma into, what is F? Sigma into A. So area is this 10 centimeter into 0.127 centimeter. Just multiply it, convert it into meter square, then use it there. You will find F, sigma into A. So as it is given in MPa, so we'll find it in mega newtons. So then just multiply it 10 to the 6. You'll get it. It is 661. It will be. So just you have to find out sigma, and then from sigma you can find out, just convert it to force by dividing with the cross section area. Okay, so this is another question. Component subject to tensile stress in a mechanical device is monitored periodically for cracks by NDT. But it can only detect cracks, both surface and internal, which are larger than 1 mm. And keeping 10% margin of safety, what is the maximum allowed tensile stress on the component? Fracture toughness is given, and crack geometry factor, that Y is given 1. Here also is pretty simple question. Use this is given as 30, 3.14 into 1 mm, that means 10 to the minus 3 meters. This is 30. So this will be 30 divided by 535.37. But it is
So
given.
it should be 10% margin of safety.
Hmm.
So sir, like the crack length should be like 1.1 into 10 to the power minus 3 now, like 10% extra.
No, crack length we can't control now. We can control the stress levels. Okay, so margin of safety will be applied to the stress. So here it is 535.37 are getting, that is the maximum stress we can apply. So this will be 100%. So if it is 100%, we have to keep 10% margin of safety. So we have to apply 90% of this. Okay, so if
481 megapascal.
If 100 is 535.37, then what is 90? That we have to calculate. This will be somewhere around 480 MPa. Okay, so crack length we can't control now. We can control what stress we are applying. So the margin of safety is always applied on the load or the stress. Like it can take maximum this load. This is 100%. So we will not allow it to take this load because it will break at this load. So we have to keep some margin of safety, some load lower than this, so that it will not break.
Okay, sir, understood.
Okay. Okay, so in fracture mechanics, this much is enough for gate. I think this K1C relations and all those I wrote there. Is the slide visible now?
Yes, sir.
There is something wrong. It is mixing up. I don't know. Okay, this is fine. So, any questions you have on fracture mechanics? Like if you have solved any questions or something like that, you could not understand. Fracture mechanics itself is a like subject, 4 credit subject. So in 1 hour, I don't think I can teach much, but in GATE it is pretty simple. Like these 3-4 formulas, they always ask questions based on that only.
So, like you said the difference between plane stress and plane strain. So, like how exactly in real life, like we can like use it in applications.
Applications, you see, that's why we derived this formula, na? This B. If thickness is bigger than this, then you can apply plane strain condition. Then only the plastic zone size will be small enough to assume it plane strain condition. If thickness is lower than this, then you have to go for plane stress condition. And that depends on the fracture toughness and the yield strength of the material. So that will vary depending upon that. And in plane stress also we have to go like for elastic plastic materials. This is basically for elastic materials. But we're assuming this should be for elastic materials, but it is also valid for metallic materials when the thickness is high. So no, there is no much plasticity because of the constraint factor that is caused by the thickness of the material, because a large amount of material has to be deformed if the crack has to deform plastically. Crack tip blunting cannot occur much in case of plane strain condition. So no much plasticity. This condition we can apply this. Basically when the thickness is high, then there will be not, even you can see in Charpy test, impact test, if we go on increasing the thickness, the material will fall in totally brittle manner. And when the thickness is low, there will be blunting and there will be plasticity at the crack tip. This is the reason why. And also there are methods for elastic plastic materials like J integral. That is a separate thing. That is a bit complicated. And you in GATE you won't find questions from that. Just remember the name J integral. Is one method. So there you have to go like around a crack tip, you have to go like a contour and you have to go for integration and along that line. So if you go for testing a material, first you have to like, there are also specific methods to find this K1C. How to find out. If you want to read more about this, even in EduUdr, this is also given. How to find out the plane strain fracture toughness criteria. How to find out that. One hour is not enough. This is a full like 4 credit
So
course.
what will be the next week topic, sir?
Next week, 1 minute, wait. Topic next week will be material characterization. XRD I have already taught those things before. Basics of XRD, how X-rays are generated, what is structure factor and all those things. But I have not touched upon SEM, TEM, those things. So I will focus on that more. So many things are there. Like 1 hour in week is not enough. You should read also and try to solve previous year questions. And concepts must be clear. There are so many things like phase transformations, physical metallurgy itself is big. Extractive metallurgy, do you read that? Like all those, how the Mons process, Kroll's process, I just remember the names. I don't remember whatever happens inside that. Okay, so I will stop now. If you have any questions, you can ask, or I will stop now.
Sir,
Hmm.
can you hear me, sir?
Huh?
Can you hear me, sir?
Huh, I can hear you.
Sir, the question in the slide number 9, we directly assumed it as a surface crack and we took as 1 millimeter as directly as here, sir.
Slide number 9. Yeah.
As a here, they have mentioned that the entity can detect both surface and the internal cracks, but we directly assume A as 1 millimeter. Even though it can be a central crack.
No, it cannot be a center. It assume crack geometry factor of unity. Yes.
Okay, so based on that,
No, for unity, if we assume that is for center crack.
alright, sir. Then
Try this
yeah.
using 0.5 mm. Can you tell me what is the result you are getting? Because in the answer, the sheet that was mentioned in the gate here, that was given 480 MPa, I think. The answer was. So maybe if you try, like, it is given that both surface are internal, so we can assume anything, I think. But if you go for crack geometry factor, it is unity for center crack only, not for side crack.
The maximum comes around 757, like without the factor of safety.
Okay, then that will be much higher than that. The answer sheet it was 480 MPa. So according to that, this only matches. Like if you take directly 1 mm. But if you see the crack geometry factor, if it is unity, then it should be a center crack.
So which one can be solved? We have to compute both and see which comes out to be the maximum. Or
But in this, like, no option is given, only a numerical type question. And the answer key was 480 MPa, I remember. 480 or 481, something like that.
okay.
Okay.
Like which cases we can take as directly as the length and dividing by 2.
But even if you don't get answer, you can challenge this type of questions. Like if the crack geometry factor is 1, then it should be side crack, like a center crack. So we have to take half of it.
Sir, and also the K1C relation which we saw with sigma root pi a. This is for plane strain conditions, sir. Or for the place for any cases.
No, this is for all condition, plane strain condition only, because we are calculating stress intensity factor in plane strain condition only.
Okay.
So this is only for plane strain condition.
Okay, sir. Yes, sir. Thank you.
Okay. See you next week.